Okay, so a few people just joined. What I was saying is we're going to be doing a simulation today. So I'll guide someone. It's much easier for me to guide rather than bouncing between screens. So who would like to do the simulation?
I could do it.
Amir? Okay, good. So we've got 8. I think last week we had 9. Let's see if one more person joins. Okay, Joshua's here. We can start. Okay, so we're going to do our design. And if I haven't given you permission to record, if I passed you over, let me know. So, oh, we got 10 participants. Who else just joined? Okay. Let me see if I can get. Okay. So anyway, we're going to do our last design project. So it's basically a continuation of the Lab 7, where we made the emitter follower amplifier. And so what I'll do today is I'll just go over an example of the calculations. If you haven't done it yet, maybe this will be helpful, or if you already have done it, it might be useful just to check your work. And then we'll do a simulation, we'll build it, and we'll go through the simulation steps. Okay, so this is some notes. These are on Moodle. This is for like configuration number 6. So for this configuration, before I go on too, it's important that you complete this lab and hand this one in. This one's heavily weighted compared to the other ones. So like, for instance, if you're in an A and you blow this one off, your grade may drop as low as a C. I forget how it's weighted. Professor Headley actually set it up. But yeah, if you're getting a low A and don't hand it in or do a poor job on this one, it can easily knock you down to a B. So you want to make sure you do hand this one in, do a good job. Okay, so anyway, just going through the design. In the lab instructions, it talks about the 2N2222 transistor. In our, we have like a 2N3904. That should work for you. You can look up its pinout on the on Google to see which is the emitter and the base and the collector. So, and I'll do a build example of it next week. Okay, so for this particular design, this was number 6. We have the load resistor is 4.7K, the gain is 10, the supply voltage is 10, and then the minimum, the swing peak to peak is 2 volts peak to peak, and then Rn is equal to 12 K ohms. I apologize for my poor writing skills. Okay. So, I mean, classically, this is the way I was taught to look at these things. We're going to have our output writing. If our VCC is 10 volts, we want our output to ride on a 5 volt DC offset at the collector. And then it's going to swing for 2 volts peak to peak to like between 6 volts and 4 volts. Okay, and then as far as the current's concerned, we got to make sure that we have enough current to deliver to the load, and then also deliver or bias up the transistor. So the way we start this, we look at how much current we need to deliver to the load. So in this case, we need to deliver 2 volts peak to peak with a 4.7 k ohm load. So that gives me 0.42 milliamps. So if I multiply that by 3, just to make sure I have enough current to bias all this stuff, because I have current flowing between the collector and the emitter, and then also flowing to the load. So I just got to make sure that there's enough current to do all that. So I generally multiply by 3. So I'll say, okay, I'm going to make my IC equal to 1.26. So that's 3 times 0.42 milliamps, what's delivered to the load. And then again, for maximum swing, I want to have my VC like around somewhere between 5 and 6 volts. You know, I got a 10 volt supply, so 5 is a good place to start. It's in between 10 and ground. Now, the other thing we'll generally do, I mean, you can do this at a lower voltage. I'm just going to start and I'm going to say, I'm going to make my VE, my emitter voltage, 10% of my supply voltage. Now, you could actually go down even lower. You could make it like 5%. But in this case, this example, this will be enough to give us a 2 volt swing. Because again, we're going to have VE is going to be down here at 1 volt and VCC is up here at 10. So conceivably, this thing could swing. If my emitter's here, it's going to start clipping when it tries to swing as low as 1 volt, and then it's going to start clipping when it tries to hit gets close to 10 volts. And we'll check that out when we do our simulation today. Okay, so the first thing we got to do is figure out, okay, what is my collector resistor? So I'm saying that I've got 10 volts here, 5 volts here. So I've got a 5 volt drop across the collector resistor. So I'll say 5 volts divided by 1.26 milliamps. And that again is 3 times the load current. And I get from that 3.9 k ohms. And that's a good value. That's a standard value. Actually, let me do the math again and see where it is. 5 divided by 1.26. Okay, so when I calculate, it's 3.968. So that's a standard value. Actually, let me grab my kit and see if we have those in the kit. So, I mean, that's one thing you want to look at too, if you can. Yeah, in the analog discovery kit that I have a 4.7K and a 2.2K. So to get to 3.9, I might have to use like a, if I were to use a 2.2K and a 1.5K, that would take me to 3.7, which is probably good enough, but I'd have to probably put 2 resistors in series, or 39 times 2. I don't think I have anything in there that I could put in parallel. I could probably put something in parallel with 10 k ohms to get something close to 39 as well. But you do want to kind of think about what resistors you have available while you're designing this thing and try to round up or round down, whatever is closest. Okay, but anyway, we've established that my RC is going to be 3.9 k ohms. And now for a gain of 10, I want 3.9 k ohms divided by REA is equal to 10. Now, actually, we'll find if we do that, our gain is actually going to be much lower. I think I'm going to make a modification here right now, because effectively, I did this way, but this is an iterative process. We'll build it, we'll simulate it, and then we're probably going to have to tweak our design, most likely change REA to get the gain and the signal swing we want. But I'm going to do something right now that's kind of off script here, because effectively, okay, I've got a supply voltage here, and a DC supply has big capacitors on its output to filter out any ripple or any noise coming out of the supply. So from an AC standpoint, not a DC standpoint, but from an AC standpoint, this node here is essentially at ground. Okay, So effectively, I've got RC in parallel with RL. So let me see what the parallel combination of that looks like. 4.7 shift inverse shift memory in plus 3.9 shift inverse plus memory recall equals shift inverse. That would say that the parallel combination of those two is actually 2.13K. So I'm actually going to put a note on here if I can. Let me see if I want to insert a note. Do some modifications here right now. Okay. RC parallel RL is equal to 2.13K ohm. So for a gain of 10, I want REA is equal to 2.13 slash 10, which is equal to, we'll just say 200 ohms. And let's see, in my kit, I've got 100 ohms. I'd have to use like two 100 ohm resistors in series. But actually, I'm going off script from what I wrote out here originally. And but I think this will get us to the game quicker, get us to the game we want faster if we just make this design change. So now I'm going to set REA equal to 200. Okay, so now I want my VE, oops, come on. I want my VE to be 1 volt. And I've got 1.26 milliamps because my emitter current is essentially going to be the same as my collector current. So now I set up this equation where, let me scroll down here. 1 volt divided by 1.26 milliamps gives me 739 ohms. And now if I take away the 793 ohms. 793 minus 200 equals 593 or 600. So actually, I'm going to set REB to 600. Did I paste? Let me try that again. Paste. Oops. Oh, come on. Oh, come on. Let me try this again. Copy, paste. Okay. This is going to be 600. Okay. And then let me do that again. Fly. Okay, so I've established that my REA is going to be 200. My REB is going to be 600. Okay, so now I've got 1 volt here. And then in this case here, it looks like you could estimate VBE, base to emitter voltage, across that junction to be 0.7 volts. It looks like here, when I originally did this, I said it was 0.6 volts. I've got 1 volts here. I go up 1.6 volts. And that's my base voltage that I want to establish. So now, oh, by the way, as far as capacitors are concerned, let's just use something close to 10 microfarads for each one. Something greater than 1 microfarad will suit it. As we'll do, we'll experiment in the simulation to see where the high pass cutoff takes place. And so that's very much dependent on the capacitor. For the practical, let's see, in our kits we have two 10 microfarads and then we have a 22 microfarad. So what we'll do is we'll figure out when we do our simulation which is the dominant one, which is really setting the high pass cutoff. And then that one could be 10 microfarad. And then for the other ones, you can just make them 22 or 47 or whatever else you have in your kit, something higher. But anyway, so as far as the caps, just for your design, just put in 10 microfarads. And then I wrote here IC divided by beta. I'm assuming my beta is 100 is equal to 12.6 microamps. So I've got 1.26 milliamps going down the collector, and then my current gain is 100 assumed. That's probably the lowercase too. It's probably most likely 150 or 200. But anyway, I just use 100 for that. And that's not so much too important. It's just that we're going to put together a resistor network here to bias the input. And we did this in lab 7. And we just need to make sure that we have enough current to set up the biasing and then also to deliver 1.26 microamps to the base. Because again, these bipolar transistors, like the FETs were voltage controlled, these are actually current controlled. So the current swing here will manage the current swing through from the collector and emitter. Okay, so I need a 12K ohm input resistance. So I have this one equation for parallel resistors. Oh yeah, let me back up there. So again, we have the similar condition here, where this is essentially a ground, this DC. From an AC standpoint, this point here is essentially a ground. So these two resistors are basically in parallel, and they act together in parallel to create the input resistance. The input to the base, there's little current flowing through there. It's microamps. It's going to be a relatively high impedance compared to these two here. So we can ignore that input resistance of the transistor itself. So, but again, the point is for our RN, if we need 12K, which is the spec, then we can consider these two in parallel. So now to calculate those, we got 12K is equal to R1, R2 divided by R1 plus R2. That's the parallel resistor equation. And then we also have that we want our base voltage to be 1.6 volts, which is equal to 10 volts times R2 over R1, R2. So that's a voltage divider equation to set that base bias voltage. So we work through the math here. We multiply R1 and R2 times 1.6, and we got 10 R2 over here. And then we can simplify it. And then I came up with R1 is equal to 5.25 R2. And then I plug that back into this parallel resistor equation. So I have 12K is equal to 5.25 R2 times R2 over 5.25 R2 plus R2. And then I multiplied that out. I got 63,000 R2 plus 12,000 R2 is equal to 5.25 R2. And then I calculated 75,000 is equal to 5.25 R2. And I calculated R2 is equal to 14.28 ohms. So we could basically say 14,285 ohms. So basically 14K. And in my kit, let's see, what do I have? I have a 10K and I have a 4.7K. So I'd probably put those two in series to create that. And then I have my R1, the one that goes on top, as 75,000. And in my kit, I have a 68K. And let me see, 68K. And then I have a 6.8K. So I could probably put those in series, and 68 plus 6.8 That'd give me 74.8K. So that would be a good one too. So I could put series resistors to create these values. And then if I just to check, I'll take the parallel combination and I get basically 11.99. So that's approximately 12K. And what am I doing here? Let's see, 8.4 volts divided by 75. I'm not sure what this math is. I did this like a couple of years ago when. I don't know where this 8.4 is coming from. I think I know what it is. It's this is 10 volts minus 1.6 volts is how I got to 8.4. And then my R1. So basically what I'm looking at there is what's going through this resistor here. So I'm saying I got 10 volts here. I've got 1.6. So my voltage drop through R1 is 8.4 volts divided by 7.5K. And that gives me 112 microamps, which is roughly equal to 12.6. Well, it's close to being 10x of what the base current should be. But what that's telling me, I need 12.6 microamps feeding my base. That's my IB. And so I've got 112 microamps coming down through that R1. So that's enough to bias the two resistors that set the base voltage, as well as drive current into the base of the transistor. Okay, those are basically my calculations. I'm going to hand over this screen to Amir. Oops, let's see. Wrong button. I'm going to stop sharing and then hand it over to Amir and we'll do the simulation. Okay, good. So let's go pull some resistors in the or let's see. Let's actually search and see if we have the 2N3904 transistor. Otherwise, we'll just use the 2N22. I think we might have to go into the libraries. Nothing's coming up, right?
Yeah, it doesn't seem like it.
Okay, let's try this. Here, let me move this out of the way. Let's just try real quick. First of all, why don't you put a Q in front of that and see if anything shows up? Nothing? Okay, let's go to this little arrow down below where it says libraries, the green one where it says plus. Yeah, let's go on there. And then let's scroll down and there's probably like transistor or bipolar. Let's see if there's anything that says bipolar.
Right here.
Yeah, let's click on that, open that one. Hey, it showed up. Let's try to use that one. Okay. And before we get too far down the road, why don't you right click on that and let's see if the model is set up. So highlight it.
Oh.
Oops.
Whoops.
Yeah, click it till it all turns. Click the transistor body and then it'll all turn pink. Now right click and then there's edit model, PSpice model, a little bit farther down there. Let's see what it's got in its PSpice model. Open that up. Okay, that looks good. Let's open that up a little bit more. So it's saying if we look down here, our BF, what's our BF?
416.4.
Oh, that's high. Okay, good. We'll use that guy. So otherwise, if you're doing this and you're having a hard time finding that, you can also look for the 2N222. But I mean, what you saw is we went into the model that said bipolar. And if you just simply type in 2N222, 2222, and it doesn't show up, try putting a Q in front of it. And that'll, a lot of them have Qs as part of the reference designation. Okay, so let's see, we need 1, 2, 3, we need 5 resistors and you can make them all vertical. The analog, yeah, there they go. 5 resistors and 3 caps. Actually, we need 6 resistors. You can make those, that one, make that one horizontal. And then the other one, the one by the load, you can make, put one down at the bottom near R8 and make that one vertical. Yeah, move it to the other side of R8 or R6 rather. Yeah, and then you can keep that one vertical too and put it down by R4. We'll make R4 R, yeah, that's okay. Well, okay, let's kind of organize things and wire this up and see what we still need. So yeah, you've got R1 and R5 can be your the base bias resistors. And then where you got R2, that can be your collector resistor. So that can touch that can touch the collector there. Actually, just yeah, right there. Good. Yep. Oh, you might need a longer.
Yeah.
Okay. And then we'll have R6 can be REA. So the first emitter resistor. And then we'll put another resistor below it, and that can be REB. So you can go select maybe R4. Good. Yeah, yeah.
Come on.
They don't want to touch like that, huh?
Yeah.
I don't know why. I think I've touched them in the past, but anyway. And then let's put C2 parallel to R4. Okay. And then the ground, yeah, those connect across. That's good. And then the bottom of that connects to the ground. So slightly under that bubble. Yep. Okay, good. And now that C3, let's put R3 like parallel to C2 right now. That'll be our load. And then we'll put C3 above it. No, not that connection. It connects to the put C3 above it. It was good where it was at.
Oh, okay.
And then yeah, that's good. Okay, and then you connect the bottom of R3 to ground, connect those two, yes. And then the top of C3 connects to the collector, so it connects just underneath R2. That's good. Okay. And then those two connect in series, R1 and R5. And then they connect to the base. Good. And then the top of R2 and R1 connect together. Those are the VCC. And then the bottom of R5 connects to ground. Okay. And then C1, we'll put a VAC input. So let's get a VAC and then also a battery. So from source, you probably got, yeah, that one. Yeah. I'm sorry, not VAC. Let's do V sign. It's easier, I think, to get these things tuned up and running if we start with V sign. Yeah, that one. Put it if you can to the left of C1.
Letter C1. Okay.
Or you should put it below C1, and then C1 can be vertical if you want. Yeah, and then so that the C1 will connect to the base, and that connects to C1. Yep.
And then the top of C1 into right here.
Yes. And then the V sign can connect to ground at the bottom. Good. And then we need a battery, VDC. Okay, good. Okay, let's put that to the right of everything. Yeah, that's a good spot. And bottom connects to ground, and then the top connects to the top of R2. Okay, and so we'll give we'll just work from the left to the right. So let's give the battery a value of 10 volts. I'm sorry, the right to the left. Duh.
So
Okay, we can do either way. Yeah, let's give that 10 volts. I misspoke. Okay, and then R2, let's change it to that was 3.9K. And let's change the reference designator to RC. So where it says R2, double click on that and let's call it RC. Okay, good. And then C3, let's make that 10 micro. Good. And then R3, I think our load was 4.7K. Okay, good. And then C2, we can make that 10 micro. And then R6, it was 200, I believe. And then R4, I think I had that at, let me look at my notes again. Hold on. I forget if it was 400 or 600. Okay, R4, let's make that 600. Okay, let me go back. Where's my Zoom? Oh, my meetings. I lost my Zoom screen, sorry. Where am I? Okay, hold on. I think I found it. Okay. While we're at it, let's call R6 REA and R4 REB.
RVB?
REB.
REB. Okay.
Emitter resistor B. Okay, so if you remember the way this works, the ratio of RC to REA sets the gain, and then REB is there to set the biasing, the DC biasing. But when this thing's in operation, C2 is essentially going to be a short. So REB isn't going to have much influence on the AC performance. It's just biasing the emitter. So that's all good. So now let's go to while we're at it, let's call R3. We'll call that RL. Okay. So this will look like the one that's in the lab write-up. R1 was 75K. And then R5, we call that R2, and that was 14K. Okay, and then CN, we'll make that 10 micro. And then we needed 2 volts peak to peak. So let me do this. 2 divided in a gain of 10. 2 divided by 10 is 200. So let's make the amplitude, the offset can be 0. And then the amplitude, if we make it 100 millivolts, so 0.1 volt, or 100 millivolts, either way. Okay, so that's peak. So our signal should be 0.2 volts peak to peak. And then let's make the frequency 10K. And then the AC, we'll set that at 0. And I think we pretty much have our circuit assembled and built. So now let's set up the simulation profile. Yeah, you can copy and cut that and paste that if you want. Although I think, Alex, you probably have a different design spec you're designing to, but okay. So we're going to do a transient to get this thing tuned up. So we'll go transient. And we've got 10 kilohertz. So if we want 5 waveforms, that would be 1 millisecond would be 10 waveforms. So we could just say 1 millisecond. We'll see 10 waveforms in the screen. That's okay. Okay. And then we'll do 1 micro per division step size. So that's always important. So we'll do essentially 1 micro, we're going to do 1,000 calculations. Okay. So we'll do apply and okay. And let's see how she runs. Oh, you know what? We forgot to look at what's the reference designator of our input of our signal source, V1. Okay, so we're gonna want to look at V1 plus and then VQ1 collector, C. So let's look at those two. Current, yeah. Is there V1 plus and then VQ1 C? That one, yeah. Let's see what those look like. Okay, good. So we got at the bottom, we've got our signal. That's our input. That's 200 millivolts peak to peak. And let's put a cursor on and see where the peaks and valleys are occurring on the output signal. So the peak, at the peak of the waveform on the output, that is, okay, that's at the valley right now of the output. So that's at, it's difficult for me to read off the screen. Is it 5.07?
Yeah.
And then let's see what's going on at the peak. So shift it over. Yep. Go to the very high at the output. And that is at 6 point what?
6.9306.
Okay. So we basically have 6.9 minus 5. So we basically have 1.9 volts. 1.9 divided by, and again, at the bottom there, we have 200 millivolts peak to peak. So I'm going to say 1.9 divided by 0.2 equals 9.5. So our gain right now is at 9.5. So that's probably within spec, because I think all those specs had tolerances on them. And so I think the gain spec was plus or minus 10. So we did good. We didn't have to do much of an iteration. Now I am going to go back and tweak just to help some of you, some of the other people out, because they're probably going to have to tweak their designs. Let's actually look at our schematic, by the way. Okay, so this is good. See, all the voltages lit up. And what we see, we were designing for the voltage at the collector to be 5 volts. In actuality, it looks like it's 6 volts, but that's okay. And then our base was supposed to be 1.6 volts, and we're at 1.487. That's still okay. This transistor, I think, is performing very well. You know, in the lab at the university, we use the 2N222, and its current gain is in the order of like 150. So a lot of times those fall short on the gain. And so I'm actually pretty impressed that we were able to nail this on the first time. But let's just, for example purposes, let's just play around with this and make some changes, because a lot of you may find that you still have to tweak your circuit to get the gain up to where you need. Because I mean, right now we're at 9.5. We're essentially in the 10 volt gain spec. So the way we can get our gain up, there's really two main controls. You can change RC, make it higher, or you can reduce REA. So let's just see. So we're going to make a mental note that right now the voltage at the collectors is at 6 volts. So let's change REA to like, let's just start with 180 and see what that looks like. And then we'll run it again. Okay, so you see that before we go, yeah, but you see that the collector voltage came down slightly. The base voltage didn't change much. The emitter voltage is 820. That's all good. Okay, so let's see how our gain looks now. So we'll go back and plot those two again. And for everybody out there, if you can't see really well, he's plotting VQ1C. Okay, so our peak right now is now at what does that say?
6.93.
93. And then our valley is at
Roughly 5.93.
Are you sure that's not a 4?
Well, yeah, it's a 4.89. Sorry, I was looking at the Y1, Y2.
Okay, 4.89. So we have 6.9 minus essentially 4.9. Okay, so that gives me 2, and then divided by 0.2. So that's a gain of 10. So that's spot on. But just to review, so what we did there, I think the best way to approach it is if you're not meeting your gain spec, start reducing REA in small increments and see how things change. And what you want to watch every time you change it is that you're not dropping the collector voltage too low. We designed for the collector voltage to be 5 volts. Right now we're at 5.9. So you don't want to get it like if it's supposed to be 5, it's okay like if it's plus or minus 1 volt. But like let's say if it's supposed to be 5 and it drops down to 3, what that means is it's really going to reduce the dynamic range at your output. Because if it drops down really low, you're going to start clipping early on the minimum swings or the lower swings. So I hope that I expressed that well, that you understand. But basically you're going to design for VC to be half of the supply voltage, and we can say plus or minus 1 volt. And it's best to try to keep it within that range if you can. If it's plus or minus 1.5, that's still probably good. But like if it strays without, like if you're trying to set at 5 volts and it's plus or minus 2, you need to be a little cautious there as to what changes you're making. And just, okay, so we saw that when we reduced the emitter resistor, the voltage came down. Let's just try something else just to see what happens. Let's increase RC, and let's make that let's say 4.2K and see what happens to that collector voltage. And we don't have to plot it. We'll just look at we'll just run it again and see what happens to that 5.9 volts. So if you run it again, yeah, it's going to go down too. So anyway, we don't have to plot it, but that's just showing you that when you increase RC and you decrease REA, you're probably going to drive the voltage down. And then if you want to raise that voltage, you decrease RC and increase REA, and that will most likely take it up. But for right now, we can put RC back to 3.9K. Okay, so this is looking good. We've basically got this thing tuned up. And so the transient is the best way. So now I'm going to look at the instructions to the lab. Hold on, let me jump screens here. So in the lab, it says, okay, consider, this is a SPICE simulation step 2. Consider your assigned specification and complete the first cut paper design of your amplifier. Hint, it is better to use worst case values for beta. So for instance, like if you're using a 2N22, to assume that it's like 100, but that didn't even really come into our calculations so much. And it says, enter your design into SPICE and run the simulation to determine the bias points. So those are those purple voltages we saw. And then check the simulated collector bias current. So we can turn those on too and check that. So one thing I think you want to do is when you get your circuit all turned up, is you probably want to print out your schematic with all those currents and voltages lit up. But what you're also going to do, I think the best way to summarize your design at the end is to have a table and show, okay, this is my design spec, and then report on how you did with the voltage peak to peak, how you did with the, what else? Voltage peak to peak and the gain, really. And just report how you did versus your spec. Okay, so we basically did step 2, and then we also did step 6, because it says if your design does not meet all specifications, make changes to improve and repeat steps 2, 3, 4, 5. We basically have this thing meeting its specifications. Let's see real quick. We needed a 2 volts peak to peak swing, and I think that's what we're getting. Yeah, we have 2 volts peak to peak swing right now. Actually, let me just check that real quick to make sure that's what the spec was. The spec was, yeah, 2 volts. So we're basically meeting our specification right now. Okay, let me see if I can find my way back to the Zoom call. I've got so many screens up. I've got to, where is that? Where is that? Let me do this. Okay. I think I found it. Okay, I'm back. Okay, so we've basically met our specs. We're at step 2. Step number 3. Hold on, let me, rather than jumping to the Word document, let me see if I can find my printed copy of this lab. I think the next step, we run an AC sweep and we figure out where the thing turns on. So let's do that. Let's put in a VAC and run the AC sweep. And then we're gonna find out where it turns on at the lower. We're gonna designate that by the lower 3 dB. So you don't have to change the amplitude. You don't have to change that. Those are all okay. So we'll set up a AC sweep simulation. So AC noise, yes, that one. And we'll start at 1 hertz and we'll go out to 10 kilohertz. It should be pretty much turned on by then. And then we'll do 30 points per decade. Okay, so let's run that.
Should I change this back to 200 or just keep it as is?
That's good. That we're spot on 10 gain of 10. So let's keep it there. Okay, so trace, add trace. And then all we have to do is look at the collector voltage, really.
Okay.
Okay, so this shows us the performance. So this is in scalar volts. So it says that by the time we get to 1 kilohertz and 10 kilohertz, we're at 10 volts. We could actually let's since we're looking for the 3 dB point. I mean, we could do 0.707 of the passband, or we could also express it in dB. Let's just go and do work in the dB. So let's get rid of that trace. Let's go. Yeah. Oops. Let's just run it again. Just run it again. Okay, trace, add trace. So over on the right, there's a dB there. See, go down a little bit more. We're not going to do Bode plots. We'll just go where it says dB, and then we'll put in VQ QC. That's good. Okay. Okay, so now we got a logarithmic scale. And so our passband is 20, basically 20 dB. So 10 log times 20 is 20 dB. So we have a gain of 10. So that's all good. So now let's put a little more resolution on the bottom. Let's click on that scale and change the X grid up above X grid. That's okay. Let's go up to X grid up. Yeah. And then get rid of automatic and go to 10 over to the right. So then it looks like the logarithmic scale. Okay, good. And now we want to go down 10 or 3 dB from 20. So we go down, move your cursor. Yeah. Each one of those ghost lines is 1 dB. It looks like 5, 6, 7, 8, 9, 10. Yeah. So our 3 dB occurs, it looks like at what, 92 kilohertz, is that?
Yeah, 92.206.
Yeah. Oh, those are hertz. Yeah, 92 hertz. Okay, good. I'm going to write that down because we're going to revisit that in a bit. In fact, let's just jump to step 7 because that has us do an AC sweep too. Okay, so let's just do some review. We already completed step 2 and step 6. We built our circuit, we tested it, and then in step 6 we optimized it for gain. we just ran an 80 AC sweep. So that's step 3. And we identified the lower 3dB at 92 Hertz. And then it says, does the simulated mid-band gain agree with your design calculations? And so our design calculation was for a gain of 10, and we've got slightly over 20. So yes, we're good there. Okay. So step 4, actually we should have jumped to step 4 when we had it set up for the transient. The step 4 is basically figure out where it clips. Step 5 is run a simulation that checks for the input resistance. That we'll also do in the transient. But for right now, we're going to skip to step 7. And in step 7, we're trying to figure out which capacitor and resistor combination is the dominant pole. So if we go back and look at our schematic, we've got the Cn reacting with the input resistance, which is 12K, and that's creating one pole. And then we've got REB reacting with C2, and that's creating another pole. And then we've got the load reacting with RL and RC, and that's creating another pole. So the way we're going to figure out which is the dominant pole, which is setting that 92 Hertz, is we're going to set some of these to we'll just start with CN. We're going to leave CN at 10U, and we're going to get rid of the U. We're just going to change C2. Let's go to C2 rather. And let's change that to just get rid of the U. And it's just going to be 10 farads. So it's going to be huge. And with that one too, we're going to change that one to 10 farads. Okay. So let's run it again and see where the cutoff frequency is now.
So do the same plot with dB.
Yeah. Okay, so here our 3dB point is very low. 20, 18. Oh, okay. So it's actually going to be at 17. So move it a little bit to the left, a little bit more. See that it says 18 and 16. It's going to be in between those. So right now with C1 or Cn equals to 10 microfarads, our 3dB point is what, 1.7 Hertz?
Yeah, 1.75 Hertz.
Okay, good. And then I'm just also going to make a note that with all of them at 10 micro, the FC was 92 Hertz. Okay, so now let's do the same. This is like a process of elimination. Let's go back and change that to 10 now. And then we can do that one at 10 micro. Okay, and then let's run it again. Okay. Cursor, where are you? There you are. So 17. That's essentially what we saw before, right?
Yeah, 91.35.
Yeah. So CE equals 10 microfarad, and that was 91.35. So that's the one's looking dominant, but just to make sure, we're going to do it now with the load. That's bizarre. Now, why is that like that? No, let's look at it again. I don't know why it's like that. I'm a little puzzled. I haven't seen that before. I usually see it looks like a low pass, but 10U, 10, 10. Let's look at it again.
Yeah.
Let me look at this. Let me look at the response again. I'm sorry. Let's go back there. So that's like a low pass filter. I'm puzzled by that, but anyway, look at where the gain is too. That's bizarre. That is bizarre. I frankly, that surprises me. I expected it to look like the first one we did. But I think we'll just jump to a conclusion here that the one that's defining the overall performance when they're 10 microfarad is when you make the capacitor parallel to REB equal to 10 microfarads. So that's the dominant capacitor that's setting the performance. Okay. That last display was a little bizarre, but I'm not going to get hung up on it. So let's make them all 10U again. Yeah, that was surprising. That's not what I expected to see. I did this with students in my class yesterday, and it was a little different, but it is what it is. Okay, so now we're going to V sign. I should have caught that before I had to change it. We're going to go back and we're going to do step. We're going to do a simulation sign now. Okay, so offset 0. And then we had amplitude at, what did we have it at 0.1 before? Yeah, I think it was
Yeah,
0.1.
we had a 0.1.
We can start there and just run it and then work from that. Okay. And then frequency 10K, that's in the pass band, we know. And then AC 0. Okay, so let's just run it again and then look.
Oh, wait, hold on. It's an AC sweep.
At, what's going on at QC? Yeah, we have to. It was like we were running out to 1 millisecond with starting from 0. Yeah, 1 millisecond, and yeah, it's all set up. Okay, good. Good catch.
What should I? Professor, I think I'm having a connection issue, or you're having a connection issue. I don't know, but I can't hear you too well.
Look at the collector. We don't necessarily. You can put the input if you want. Do VQ1C. Yeah, it came on my screen that I might be having a connection issue. Okay, that all looks good. So now let's jack that up and figure out where it clips. So we have 0.1 volts. Let's move it up to, let's say, 0.25 volts at the input. So let's go back to our schematic. And rather than 0.1, let's make that 0.25. So that'll give us, yeah. That'll give us 0.5 volts peak to peak. See if it's clipping still. Still looking good. It's swinging between, you've got 8 volts and you've got like a 4-volt swing over 4 volts. So it's still looking good. The top's looking a little bit flat, but let's bring it up more. We can probably just put in 1 volt and that'll just show some very dramatic clipping. Or actually, yeah, 1 volt's fine.
Oh.
Okay. So it's kind of folding back on itself, but it looks like it's clipping at like 8.1 on the top and maybe 1 point. Yeah, that's like 8.1 volts, and then on the bottom at 1.7. Okay. So that's essentially step 4. We have plenty of dynamic range. I mean, we needed 2 volts peak to peak, and it looks like we can essentially get 8 minus 1.8. We can get what is that? That's 8, 7. That we can basically get 6.2 volts out of this thing before it really starts distorting. So that's all good. Okay, last step. So what we just did there was step 4. Now, step 5, we're going to do a simulation to figure out what the input resistance we have. And the way we do that is we basically treat R1 and R2 as if they're one resistor, and we're going to put a resistor in series with that cap, C1, Cn. So we'll put another resistor in. Let's get another resistor. And we're basically making a voltage divider. Yeah, find a place to put that in there. Yeah, go to the left. It's gonna connect, yeah. And then bring R1 and R2 to the right a bit. Yeah, that's the way. Okay, now connect all those together. Okay, so the lump sum of R1 and R2, as per our calculations, should be 12 k ohms. Let's just make R3 equal to 12 k ohms as well. That's what our expected input resistance is. Okay, so if you can imagine a voltage divider, we're going to create R1 and R2. We're going to call them Z. And we're basically going to envision those as a resistor connected to ground. I hope that's not confusing. But the parallel combination of R1 and R2 should be 12 k ohms, and they are a resistor connected to ground. And there's an appendix 8.5 you can refer to, which hopefully will make that a little bit clearer. But anyway, I'm telling you right now that R1 and R2 are one resistor, and they're in parallel, and they equal to 12 k ohms, and they're connected to ground. So now I have my voltage source V4, and it's driving R3. And I'm going to assume that my 10 microfarad cap is essentially 0 at 10 kilohertz. In fact, let me punch that out. What is that? I got 10 E. Hold on a second. 10 E 6 negative, and then let me remember how to do this. Times 6.28 times 10,000 equals, and then I take the inverse of that. So that Cn should be about like 1.6 volt. Yeah, 1.6 ohms rather. So it's a very low impedance compared to everything else. So it's not really consequential. Okay, so now I've got my voltage divider, and this could probably be done as a DC as well. But let's just run. We've got let's bring the amplitude back to 0.1. Yeah.
Oh yeah.
Okay, so we have a voltage divider. So our supply voltage on our voltage divider is going to be 0.2 volts peak to peak, and we're going to measure the voltage at the base. So we're going to measure. Let's measure the voltage at V4 plus, and then the voltage peak to peak at the base on our transient. So V4 plus.
There's V1, V4.
No, go up more. I think it was higher. I think you passed it.
Oh,
There
there it is.
And then the other one is Q1B. Okay, so the red one is Q1B. Okay, so let's figure out what the peak to peak voltages of the top one and the bottom. The bottom one should be, it's essentially 2.2 peak to peak. So the top one is at the base, you have 1.5.
Yeah, 1.5.
And then the valley is
1.4.
1.4. So that's essentially 0.1 volt peak to peak. And so we have a voltage divider. We have VB is equal to 12K. Oh, no, I'm sorry. Is equal to the parallel combination of R1 and R2 divided by the parallel combination of R1 and R2 plus 12K, the new resistor we put in. So this evidence here looks, the fact that we have 2 volts peak to peak coming in and our voltage is divided by 2 to where we have 1 volt peak to peak. I'm sorry, I'm getting this all mixed up. We have 0.2 volts peak to peak coming in. And at the base, we have 0.1 volt peak to peak. That basically says that our 12K ohm resistance, the 12K ohm resistance that we inserted there is matched to the input impedance of our amplifier. And so we basically, like if you have 250 ohm resistors in series and you put a voltage on one end, in between them, you're basically going to divide that voltage in 2. Have I confused anybody, or is that clear? Is it confusing what we did there? I'm not sure. How about you, Amir? Are you confused with what we did, or does that make sense to you what we did?
It's making sense.
Yeah, because we we basically have if you again imagine R1, R2 as a parallel combination and call those Z, and that Z has a impedance of 12K ohms. Then when we put the one series with it, we're basically dividing our input down in half, and that's being indicated by our base voltage being half the value of the input voltage. Okay, and that was just step number 5. And basically we're done. We jumped around a bit, but you'll want to do that when you do this as well, because basically in step 2, 6, 5, and 4, you'll want to run a transient analysis. And then basically step 3 and 7, you'll want to run an AC sweep. And then again, when you do this, and we're going to build next week and test them, but basically what you want to do is at the end, summarize, okay, my spec was I needed this voltage peak to peak, I needed this input impedance, and I needed, what were the other specs? This much gain. You basically want to report that in a table as to, okay, this was my design spec. This is what my simulation results were. And then my test results were this. And then if there's a huge discrepancy, then you get to do some creative writing as to why they're different. Okay, but I think for today, we're basically done. Let's see, next week is going to be Thanksgiving. So we will meet again on the 30th of this month. Oh, wait, I'm sorry. I got to look at my calendar. I think it's actually December 1st, right?
Yeah, December 1st.
Yeah, okay. Yeah, our next session will be December 1st. Okay. But otherwise, I think we're done for tonight. Are there any questions you want me to address before we move on? Anybody having difficulty with their calculations that they want to review?
Wait, Professor, I have a quick question.
Sure.
For the design specs you sent last week, me and Ruben are partners, but you gave us 2 different design specs.
Okay. Well, do you want to choose one for one of them and just work on that?
Yeah, we'll take the design 3 because I'm almost done with the calculations.
Okay, that's good.
Okay, thank you.
Yeah, I'm not going to be too hung up when you hand in your report. I mean, I wrote those down and I have them, but I'm mainly just you're going to hand in your report. I'm going to look at your specs I mean, to grade this thing, I'm probably going to look at that. You have the oscilloscope plots, the simulation plots, and then I'm going to look at like if you have some kind of summary at the end as to how you perform versus your spec.
Okay. Thank you.
Okay, good. Everybody else good? Okay,
Yeah.
then have a good evening. Have a good Thanksgiving, and I'll see you on December 1st. That'll be our last session. Okay, bye guys.